Hello, my name's Gavin Bierman. I work for Oracle, and I'm very grateful to the organisers of this meeting for the opportunity to talk with you about work that we're undergoing on the Java platform. I work for a big software corporation with lots of lawyers, so I'm obliged to show you this slide to start with. Now, I thought I would actually start this talk with my conclusions, just in case I make a mess of the talk. So here are my conclusions. First is Java is not dead. The second take home, I hope, will be that we're making big changes to Java. Thirdly, we're making those big changes as fast as we can, and certainly faster than we've ever done before. And I hope to persuade you that some of these changes are of interest to you in the programming language research community. Now, the first change I need to tell you, hopefully you're all aware, but perhaps not all of you are, that we've changed the way we release Java. So before, Java was released every 2, 3, 4, 5, 6, 7 years, and that release was typically because of one big feature driver, such as generics or modules. But as you're probably all aware, the features were typically bigger and harder than we thought, and so the releases were typically delayed. We've now changed, so Java is now released every 6 months in a predictable way, so much faster than before. So we started this with Java 10, which was released in March 2018, and we've released a new version of Java every 6 months since then. So the last version was Java 16, which was released in March this year, and Java 17 will be released in September, but later. And obviously, a 6-monthly release won't have as much new stuff in it as one that took 4 or 5 years. But it has a number of positives, so you get your hands on new stuff faster, which is great. For our customers, it means that it's easier to migrate between releases because the changes are not so large, which is very useful for sort of commercial users. As a language designer, it helps us break up features into small pieces, and so we can release them, which sort of piecemeal, which is a very useful thing. And it also allows us to lay groundwork for future features. So we might release something which is there, it's a useful feature, but it's really there to support something that we know is coming up a bit later. And the other thing that we now do is we use the preview feature in the Java release cycle, which allows us to release a feature, but it's as a preview feature. So what that means is that it's just there for that release. It won't be there in the next release. You have to use flags to use it, both in the compiler and the VM. But it allows us to try something out, get feedback from the community, and then decide what to do. So we could either chuck it, or we could preview it again, perhaps making changes based on feedback from our users, or we would perhaps propose to finalize it in the next release. And we've done that with every language feature since we've changed to the new rapid release cadence. So here are some of the current Java projects, and I think these are probably the ones that are most interest to those interested in programming language research. So Project Amber, which is focusing on making developers more productive. That's what I'll talk about today. But there are 3 others that I think you might be interested in. One is Project Valhalla, which is adding value types both in the language and the VM, but also changing the generics model. It's very interesting, very difficult problem. The second one is Project Panama, which is addressing interop between Java and low-level languages like C. And the final one is Project Loom, which is adding lightweight threading model to Java, where you can have many thousands of threads running without paying huge costs. But let me focus on Project Amber. So let's consider one feature, which is records, which was released in JET 395. So this comes from an observation, which I'm sure you're aware, that in object-oriented languages like Java, when you want to define something very simple that would be a product type in other languages like Haskell and so on, turns out to be quite a pain. It's quite heavyweight to use classes for something so simple as a product of two integers. So here I've got the class point, which is just a product type of two integers, but there's a lot of boilerplate that you have to write. The question is, how do we address this in a language like Java? So obviously we could just add product types in the way that they're done in other languages, or maybe make them named in some way. But actually the right way to do this is to identify records as a special sort of class. So they have very nice syntax. So you see here in the box, the point class can now be declared as a record class, which has two components, int x and y. You don't need to declare anything in the body because the methods that you want are auto-generated for you. But you use them as if they were classes. So you declare them using new. You access them using auto-generated accessor methods that have the name of the components. So here we have accessor x and y. The components are immutable because the semantics of records kind of don't make sense if you can mutate them. So if you try and mutate the fields, the backing fields, you can't, they're immutable. And they come with the auto-generated methods that you expect, like toString, equals, hashcode, and so on. So this is an example of a feature that you want, but the answer is not to do the first thing that comes to mind. Here's another one. So if we've added product types, surely we'd like algebraic data types, so we need a sum type. So we might just leap in and add sum types in some way. But again, it turns out that the right solution, we think, is not to do that, but to approach it from a slightly different angle. And actually, the angle is about restricting extensibility. So let me explain what I mean by that. So sealed classes really address a long time oversight in the language, where if you want a class to be widely accessible, say by making it public, then it has to be widely extensible. So consider this example here of mathematical expressions. We've got this interface expr. Now we declare it to be public because we want it to be widely accessed, but at the same time we want it to be narrowly implemented, right? Just by the classes saying the same package. And here we have 3, constant, add and multiply. But if we've made it widely accessible public, then it's widely extensible. Now you can stop your own implementations from being extended by making them final, but you can't make some faraway implementation like divide. You can't stop it from implementing expr. Now, if an instance of divide were to make its way back to code that it was only expecting a constant, an add, or a multiply node, then bad things could happen. With sealed classes, you can declare a type sealed. So here we've declared the interface sealed, and that means it's still as accessible as it was, it's public, so it's accessible everywhere, but it's not widely extensible. In fact, it can only be extended by the types that are named in the permits clause in the second line here. So the interface expr declares itself sealed and also declares which types can extend it. So in this case, constant, add and multiply. If we then try and declare somewhere else a class divide to which wants to extend the expr, then this is actually a compile time error. And if you try and load such a class at runtime that's not on the permits clause, then that will be a runtime error. Now, in the examples I showed you, all the permitted types were final, but that's not a requirement at all. So here we have an example where constant is no longer final, but it's actually sealed itself, and it also declares its 3 permitted subclasses. A permitted subclass can even declare itself non-sealed in order to have its part of the hierarchy revert to being open by extension by unknown subclasses. So for example, here, the class add is now available to be extended by anybody. Now, notice that those subclasses, unknown subclasses, are not dangerous to code that expects only the 3 permitted subclasses of expr, constant, add, and multiply, because they're all subtypes of constant. So they're not a type that can't be dealt with. So you see here that we've added a union type, because clearly expr here is declaring itself to be the name of the union of constant, add, and multiply. But we haven't done it in an obvious way. It turns out that in this way, we get the effect that we want, but it's much more Java-like in its approach. And you might wonder, well, does this actually happen in practice? So here's an example. Constant desc is a class in the Java API. It's used for reflection. And if you look in the documentation for this interface, it actually says, hey, I am this interface. There are a number of classes that implement me, and here they are listed. And I would really like you not to implement me at all. These should be the only types that implement me. If you want to implement me, you should implement one of my subtypes. So that is screaming out to be a sealed interface. So in fact, in Java 17, that's indeed what we've now done. So we've sealed the interface, and now the types that were listed in the comment are now actually declared and enforced by the compiler in the runtime. And that type that you're supposed to subclass, if you want to declare a subclass of constant desc, is of course now declared non-sealed. So that's now your place in the hierarchy to declare an implementation. So let me show you another feature that we're busily adding to Java, which is pattern matching. And again, we're using this feature of previews and of smaller increments to language to release pattern matching as a set of features. So we've released 3 so far, and we've got a number of further ones in the pipeline. I'm sure everyone knows about patterns and pattern matching from their favorite functional language, but in case you're rusty, a pattern embodies a test, and pattern matching is the process of comparing a value with the pattern, with the test, and deciding if it matches or it doesn't match. And if it does match, the pattern may contain some placeholders, which are variables, and they're initialized with values in the process of pattern matching. And I think it's really one of the superpowers of functional programming languages. Use it all the time, and it leads to very compact code. Been quite a few attempts to add it to object-oriented languages, but we think the way we've done it is it's a slight twist on existing proposals. And the first question actually that we were faced was where to add it. So your first thought might be to add it to switch. But at the time, switch was quite a weak statement form in the language. So in fact, it was only a statement form. There were no switch expressions. So we decided to, in fact, set up a process of extending the language to support switch expressions and so on. And while we were doing that, we looked elsewhere where we could add pattern matching. And again, I think we ended up with something perhaps not so obvious at first glance. We realized a good place to put pattern matching was in the instance of expression. So let's take it slow. Let's add the simplest sort of pattern, which is a type pattern. So here I've written a type pattern integer I. So clearly the test is the value, can it be cast to the type integer? And if it can, then I would like to initialize the variable I with that integer value. So interestingly, and perhaps obvious to those of you who've written Java code, people do this sort of operation of conditional testing against the type all the time. So Java code is littered with code that looks a bit like this, where you have an object, you want to see if it's a string, and if it is a string, you want the string value. So what you do is in the then block here, we then have to cast string, which is annoying because we know it's already a string because we passed the instance of test, and then we have to assign it with this local variable f, and then we can use that string value f in the rest of the then block. And what we realized is that if we extended the instance of expression, so the right-hand side was no longer just a type, but could be a pattern, so a type pattern in this case, we could then drop the cast and the local variable declaration completely. So you can just write a pattern on the right-hand side, and then if the pattern matches, f will be initialized with that string, and you can just go ahead and use the f. And with this feature, we can remove, let's say, 95% of the world's casts. So lots of casts disappear from your code base if you use this simple instance of pattern matching. Now, interestingly, by adding pattern matching to an expression form, we were faced with some problems that perhaps you might not have thought of initially. So in Java, the scope of a variable is very simple. So scopes are typically bound to statements or to blocks. Now, for this case, we have a declaration of a variable f, but what's its scope? Well, it's not so simple, right? Let's consider a slightly more complicated example. I've got that instance of with a pattern, but it's embedded in a conditional. Indeed, a short-circuiting conditional, so we know evaluation goes from left to right. So what's the scope of this pattern variable f? Well, it's clearly to the right of the conditional, so I'd be free to use f in that conditional. Here I'm using it to check the length of the string, and it's clearly in scope in the then block. It's clearly not in scope to the left of the conditional. That would be a bit weird. And it's clearly not in scope in the else block. So this is a scope that isn't simply rectangular like they are normally in Java. It's kind of non-contiguous, sort of holes. And we can go further. What if that pattern instance of was contained within a negation? Well, clearly in that case, the string f, which should be in scope for the else block, because you only execute the else block if the pattern matches. But it's clearly not in scope, shouldn't be in scope, in the then block. So we now realize that actually the scope ought to be flow sensitive. Of course, you know your De Morgan laws. So what if you put it in two negations? Well, clearly then it's only in scope in the then block and not in the else block. So it really is flow sensitive. It's very sensitive to the expression that it's contained within. If it's inside a disjunction, if you think about it for long enough, you will realize that it's not in scope anywhere because you don't know which one of the disjuncts was true. So you cannot be assured that the pattern has matched in either the then or the else block. So in fact, you can't use it anywhere. And peculiar to Java, we have an if-then statement. Now, if the pattern match was inside a negation and the then block had a statement that was whose evaluation was abrupt, so it completes abruptly, and this is very common Java programming style. You put this at the start of a method. So you say, if it's not of the type I want, then return or throw an exception. Now, if you look at this program for a moment, you will realize that the only way to reach the statements after the if-then statement is if the pattern match is true. So it seems reasonable that the scope of the variable now escapes out from this containing statement and flows into the subsequent statements, given that the body of the if-then statement completes abruptly. So there's the only way to get to the statements following the if-then is if the pattern match is true. So we need to think of the scope as really very sensitive flow relation. Now that's odd, but it turns out that Java already has two flow analysis declared within it. So inside the compiler, and if you look inside the spec, you'll see in chapter 16, there's a whole chapter on definite assignment, which is a flow sensitive static analysis. And in section 1421, there's a flow sensitive static analysis for defining unreachable statements. So we're going to have to define a similar one to define this notion of scope. And here we actually use a very simple relation defined over syntax. So this is pretty much how we defined it in our notebooks before writing it up in spec speak and put it in the compiler. So the idea is to define a relation over Boolean expressions that returns two sets of variables. One is the set of variables that would be introduced in scope if the expression evaluates to true, and the other one is the pattern variables that be introduced into scope if the expression evaluates to false. And then you just define a relation over the syntax of the expressions in the obvious way. So for example, the instance of expression, well, if it evaluates to true, then the variable is in scope. And if it evaluates to false, then no variables are in scope. And then we use intersection and union in the definition of conjunction and disjunction. And for negation, you just flip over the sets. And you can use this then in the typing of a conditional statement. So you type the expression, you get the true and the else set, and then the branches get the appropriate set. So this is an example of us using a bit of programming language theory to get this definition correct. So once we've done, once we support pattern matching, for instance of, we obviously don't want to have the code that we got on the left with lots of nested if an instance of checks. We would like to extend switch, which we now have switch statements and switch expressions, to support patterns in the case labels. So a case label is no longer a constant, but a pattern. So as I said, we introduced a new label, which is case pattern. We've lifted some of the restrictions on the types of the things you can switch over. We've added a new null label, so it's no longer the case necessarily that switch throws a null pointer exception if the thing you're switching over is null. If you have a case null, then that will match. And interestingly, we realized that we get a very nice interaction between pattern matching the switch and those sealed classes, the sum types that I showed you earlier. So let me show you how that works. So already, if you declared an enum class, then and you switch over a value of the enum class. So here I've got enum e, that has three constants a, b, and c. If you switch over it and you have a case for a, b, and c, then the compiler doesn't ask you to define a default clause for this switch expression because it knows that the body of the switch is exhaustive because it's got a case for a, b, and c. Now, sealed classes are really one level up in the value type hierarchy because they're sum types. So if you're switching over an interface I that has three permitted subclasses A, B, and C, if your patterns cover the types A, B, and C, then you're exhaustive over that sum type, so you don't need to write a default. Now, we plan to extend pattern matching to structural patterns. So, for example, if you have a record class declaration, such as the one I showed you earlier for points, then you can declare a record pattern, which tests a value to see if it has the type of the record class type. And if it does, then it starts matching the structure of the values. So in this case, we are extracting the components. But of course, that thing inside could be a pattern itself. So for example, if we had the declaration of a rectangle, which consists of two colored points, which themselves are records, which consists of points and colors, and point, remember, is also a record, then in this method here, where I want to print the x coordinate of the upper left point of a rectangle, then I can use a triply nested record pattern to extract the value x. So I've got this pattern rectangle containing a colored point, containing a point, and then we can extract the value, the component values. Now, really, the thing here is what we don't have to write. So writing equivalent code today over record classes is considerably more ugly. You would have to write it as follows. And really, the problem here is that when we access values from a record, you have to worry about whether the record or any of its contained record values are null. Because if you then use an accessor method on one of those, you might get a null pointer exception. Now, with pattern matching, you don't need to worry about nulls so much because a null doesn't match the record pattern. So it just doesn't match. You don't get any exceptions. So it's very nice. But we don't want to stop there. We want to go much further. And you can Google for some documents that we've released, sketching out where we want to get to. But really the point here is, interestingly, a duality. We think that there's a duality between constructor of a class and being able to pattern match over it. So we might call that a deconstructor. So just as you can declare in a, and I'm talking about arbitrary classes here. So for an arbitrary class, you can declare a constructor, which enables you to build values. Then we think there should be a dual notion, a deconstructor, which contains code, which explains to the compiler how a value of this class can be deconstructed using a pattern matching, using a pattern. And so here I have an example of an object being deconstructed using this deconstruction pattern. And the implementation of that is declared in this deconstructor. Now, of course, constructors are not the only way to define, to build values in Java. A popular way is to use factories. So for a factory, which is another way here, my complex class supports another way of building complex values, which is using the polar coordinate system. And we think there should be a dual form of that too, which essentially is like a view. It's like another view. So here I've declared the polar view on a complex value. And you can again use this using pattern matching. And this enables us to write more compact code. So for example, if I want to multiply two complex numbers, I remember from my maths days that multiplication is much more easily declared using the polar system. So I just pattern match the values to get the components, and then I use my factory method to build the answer. Now, of course, we might go even further and extend the language so it supports patterns in assignment. And then, in fact, the code becomes even more clear. You use pattern assignment on those two complex values to get them in polar form, and then you return the factory method construction of the complex value. So let me conclude, but of course, you know my conclusions. Java's not dead. We're making big changes to Java. We're making them as fast as we possibly can. And some of them, I hope, are interesting to you in the programming language research community. And let me just wrap up in the last few seconds with some sort of more personal thoughts about language design for a language like Java. So I hope to have shown you that really the point here is trying to find a good fit with existing features in the language. Another issue we have to deal with is compatibility. Our budget for breaking changes to language is very, very small. We don't rule it out, but it's highly unlikely. We can't break things. We've got so many users, so many important pieces of code. We can't break features. So we have to work around the language that we have. And indeed, I like this quote from Peter Senge, today's problem comes from yesterday's solutions. So a lot of the great features from previous versions of Java really hamper what we can do. We have to work around them. And sometimes that's extraordinarily difficult. And I am, of course, self-aware enough to know that future designers of Java will be saying the same thing about features that I've worked on. I think, interestingly, interaction between features is both where the problems are, so it's where unexpected issues arise, but also where the solutions are, where we see features coming together to do something really nice, like that switch over SIP classes. That gives you a lot of confidence that the feature is really hitting a sweet spot. And also, I want to encourage you by saying that, we use within the Java design team, we use formal methods, typing rules and such like all the time to understand both the problems and the solutions that we're dealing with. So at that point, I shall show you my company's mission statement and I'll wrap up there. Thank you very much.